We're going to do lesson 4.2, which is critical points, local maxima, and local minima. So a local maxima, if we remember how we did it in the past, is we took the derivative of the function and found out when the derivative is equal to 0, and that would give us our critical points, and we would test our critical points. So it's going to be along the lines of that concept again, right? So let's do this. It says that a function f has a local maximum at x equals c if f of x is less than f of c, or it's when it's actually really close to it. The three scenarios that we'll be focusing our attention on in the lessons are the stationary point, which we've been doing up until now, which is finding derivative of n equal to 0, which gives us our turning point. There's going to be the cusp point, and the last one is going to be the corner point. So it says that f of c is called the local maximum value, and c and f of c is called the local maximum point. When we're actually comparing the values, and we've done this, we have our critical point and we have our f of x's, or two values or 2 points that we can actually test on either side of the point. And what we'd see is that the f of x's that we chose should be less than, and y values should be less than our f of c. The same principles would apply for a minimum. We have our f of c here on either side. We can test values, and we would see that the f of c y values are greater than the the f of x y values are greater than the f of c y values. The next thing we're going to discuss is two different kind of concepts. When we have a critical point, but the critical point, the tangent line may or may not be equal to 0. So in the first example, we have a stationary point. And a stationary point, again, the tangent does equal 0. But if you look at the actual function itself, the function has no maximum, nor does it have a minimum. So that one's considered a stationary point. The second scenario is an infinite slope point, and the way that is found is by taking the derivative, trying to x equal to 0, and it gives us something that's not defined, some kind of error, like 2x is equal, negative 3 is equal to 0. So it's a false solution, so therefore it produces, it can produce an infinite slope point. The next situation, again, the critical numbers was what I just talked about above. It's talking about the same thing. We can see that we have our critical numbers and our critical points. These points are neither maximum, critical points can either be a local min, a local max, or neither. So we have to actually do some more checks. So the check would look something like, I'll explain a little bit later on. But in this case here, what we'd notice that when we're doing this here is that the values of y are decreasing up to our critical point, which we can solve for, and then they continue to decrease right afterwards. And the same thing happens with the other ones. We can see that our values are increasing up to a certain point, and they continue to increase right afterwards. The way around this is what we're going to probably do is do our first derivative, second derivative. We'll do some calculations. What we're going to do is get the two values that repeat for our first derivative and second derivative, so we're not sure. So we have to go back to our first derivative test. And if you remember, the first derivative test says let c be a critical number, and it has to be for a continuous function. And what will happen is if we do our first derivative test, we actually check our signs, and the sign will go from positive to negative. And if it does that, we know it's going to be a local maximum at c. All right, so here's our f prime of c. Our derivative test says, this part value when we test less than the value of c is going to be greater than 0. It means it's increasing. And when we test our f prime of c a little bit to the right of f of c, the values will be negative, which means it's decreasing, and the same content will apply for the infinite points and the stationary points and the infinite slopes. And the opposite is going to be true. If the sign goes from negative to positive, then it's going to be a local minimum for the same reasons. If f prime of x does not change, the sign does not change, then it has either no local maximum or minimum. So we can see that there's our critical point, the highlight, and we do our first derivative test. We see that our first derivative test shows that it's going to be less than 0 on the left, and then it's going to be less than 0 on the right, implying that it's going down and going down all the way through. So therefore, there is not going to be a max nor a min. And the opposite will be true if it's greater than 0 for both sides. This is basically a summary of what we just talked about, the first derivative test again, and we've done in the past. The first derivative test for a relative maximum, this is supposed to say and minimum, and minimum points. So let C be the critical number we can find by taking its derivative. We're going to compare the signs. If f prime of x changes from positive to negative at C, then we're going to have a maximum. If f prime of x changes from negative to positive at C, then we're going to have a minimum. And if the sign does not change, we have neither a max nor a min. If a value of C is in the domain of the function f of x, and its value is such that f prime of c is equal to 0, or f prime of c does not exist or is undefined, then the point c and f of c is called a critical point to the function. So they're all critical points no matter what we do. A critical point locates either a relative maximum value of a function, a relative minimum value of a function, or neither. So the max or min will be that's the obvious one, or neither will be the corner of the cusp. Critical points occur when you have f prime of c is equal to 0 and gives a horizontal tangent. That's the ones that we've been used to. Other critical points occur when we have f prime of c that is undefined or does not exist, and it gives us locations of either vertical tangents and cusps. Now, on the example below, it's the color didn't come out very good, so I'm going to change it. We can actually see that there's a vertical tangent right there. Right? So somewhere there's a point where it transitions. Due to the symmetry of the function, it transitions at 1 and 0. So if we were to take its first derivative set equal to 0, we would get something that's undefined. We've seen this graph for the second one. We've seen this graph on our last evaluation. That's one of those graphs that look like to the 2/3, right? X1 to X1 2/3. So if I had to call this something, we know this is going to be the situation where we have a vertical tangent. And this is going to be our cusp, which I don't know how to spell cusp yet. Let's do an example. In this example, the table is already all set up for you, so we're just going to highlight the big items. So we can see we have the graph, and we can actually figure out what the vertex is. So our vertex here is 4 and 16. And I want to come up with an equation, take its derivative, and then test to see if 4 and 16 is actually going to be a max or a min. So a little bit of work involved, but we can do it. So we have y is equal to a x minus h all squared plus k. I'm using vertex form instead of standard form because it's easier to take the derivative of, less steps. I'm going to plug in my vertex. So we have y is equal to a x minus 4 all squared plus 16. And I had to solve for a now. So I'm going to solve for A. There's lots of ways of solving for A. I could take another point, for example, 0, 0 or 8 and 0, plug it back in, solve for A, or I can use my knowledge of the step pattern. And I'm going to choose the step pattern because it's something that we don't practice enough, right? So the step pattern works like this. I'm going to start the vertex, which we know it's 4 and 16. From the vertex, what I'm going to do is I'm going to move either to the left or to the right 1 unit. So I'm going to move over 1 unit. And then we're going to go up or down until we hit the graph. So I go down to hit the graph, I have a point there. And that value there looks like, if I look at the scale, it's going up by 2s for each box. So that looks like it's a 1. So my next vertical step should be the next odd number. So we'll go 1, 3, 5 and everything. So if I go over 1 and go down 3 and hit a point on the graph, I'm pretty convinced that our A value is negative 1. So negative meaning goes downwards, 1 means it's the A value, and then it follows the vertical step. So following that process, our next vertical step should be 5 or down 5, right? So go over 1, go 2, 4, 5. So I'm convinced that A is equal to 1, negative 1, sorry. So let's put that into the equation. Now I can take its derivative. So when I take its derivative, it looks something like this. Take the derivative of the whole entire function, so it's going to be negative 2, x minus 4, and 16 is a constant. Well, I can multiply by the derivative of x, so it's times 1. All right, so when I clean this all up, I'm going to have negative 2x plus 8. And we always trying to solve for y prime equal to 0, and that happens when we have negative 2x is equal to negative 8, or x is equal to 4. And that's how I got the 4 in the box there. Now what I have to do is take its derivative function. So we have derivative function, which I'll write down here again, which is y is equal to, y prime is equal to negative 2x plus 8. And what I'm going to do is plug in a value less than 4 into the function. So I'm going to put y prime of, well, it's 4. I'm going to put 3. So if I plug in 3 there, what I'm going to get is negative 2 times 3 plus 8. And what I'm going to see is that this is equal to 2, which is greater than 0. So that means that it's going to be increasing. All right? And if I do y prime, a value slightly greater than 4, I'm going to put 5. I get negative 2 times 5 plus 8, which is equal to negative 2, which is less than 0, so it means it's decreasing, which matches what we have on the chart. So we have f prime of x is greater than 0, so it's going to be increasing, and then f prime of x is less than 0, it's going to be decreasing. All right, let me color code that for you. So the first one is going to be increasing. The second one is going to be decreasing. The second example is pretty much the same thing. We can do it in vertex form. We cannot do it in standard form. Sorry, we cannot do it in factored form. We can prove it the exact same way. Just the opposite thing is happening, right? So I'll leave that for you to mull over. The next example says, sketch the following curves, applying the concepts presented. So let's figure this out. The very first thing I'm going to do is always plot the easiest thing. So the easiest thing to plot in this case here would be the y-intercept. Okay, here's my y-intercept. And we can prove that by letting x equal 0 and just solving what the y value is. But I think we're pretty good. So that's my y-intercept. I'm going to say it's going to be 0 and 1, my y-intercept there. And then what I got to do is I got to use some common knowledge of what's going on, right? So I'm going to give myself a little sketch. And here's my quadrant 1, quadrant 2, quadrant 3, quadrant 4. And we know that the function is a cubic. It's positive leading. So it's going to start somewhere in quadrant 3, go up, do some kind of turn, come back through the y-intercept, and do another turn. So it may look something like this. Again, this is only a sketch to give us an idea what the curve should look like once everything is done up properly. So let's start doing our calculations. The first calculation I'm going to do is I'm going to take its derivative. So we know that f prime of x is equal to 6x squared minus 6x minus 12. And I'm going to set that equal to 0, but the numbers are big. So what I'm going to do is I'm going to factor out a 6. And using the product sum method, I'm looking for two numbers when multiplied together give me -2 and add together to give me -1. So +1, -2. And then we say that f prime of x is equal to 0 when we have 0 is equal to 6x plus 1, x minus 2. And in this case here, x is equal to -1. In this case here, x is equal to 2. So those are our critical points. So we actually have to find out where exactly they are. So what I'm going to do is I'm going to say f of -1 is equal to, plug it back into the original function. So we have 2 times -1 cubed minus 3 times -1 squared minus 12 times -1 plus 1. And we're going to get that f of -1 is equal to 8, which produces our critical point of -1 and 8. I'm going to plot that in. So -1 and 8. It's right over there. So -1 and 8, kind of hard to see, but -1 and 8. And do the same thing for the next point, which was 2. So f of 2 is equal to 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 1. And I get f of 2 is equal to, if I push it by my calculator, -19. So we have 2 and -19 as being another critical point. Excuse me. So 2, -19, and plot on the graph. It's right down there. So we have 2 and -19 is my second critical point. The other thing I could have done is really use our factoring techniques that we've learned in advanced functions, do some test values, plus or minus 1, plus or minus 1/2, and then use long or synthetic division to factor it out until we got all our x-intercepts. I'm pretty sure the numbers are not nice, so we're going to leave it alone for this example, and we'll introduce it in another example. So the next thing we're going to do is the chart. So what I'm going to do is I'm going to write out the function that we're going to be focusing on. So we're going to be focusing on f prime of x, which was 6 times x plus 1, x minus 2. And I'm going to create the chart. And I may need to add more lines. Okay, this is a work in progress. This is as live as it gets. I think this should be enough. And we need one for the interval. We need one before the first critical point. We need one for the critical point, one after the critical point, and maybe it's enough. Let's see what happens. Worst case scenario, we just add some more, right? So the very first cell is going to be an interval. And we're going to do f prime of x first, and then we're going to do f of x. The second thing we're going to put in is our critical points. Keep in mind we have to leave one blank first. So our first critical point, our lowest one is x equals -1. Leave a blank. Our second one is x equals 2. So we have more than enough. I can actually space it out if I want to a little bit more. And here we're going to have x is less than -1. This is going to be where x is less than 2 and greater than -1. And this is where x is greater than 2 and the rest is extra. So what do we know so far? Well, we know that our critical points occur at -1 and 2. So if it's a critical point, in our cases here, our f prime of zeros are going to be f prime of x at those values will be 0 for the slope. We actually calculate what the critical points are for x equals -1, and we calculate it to be 8. And for x to be equal to -2, it's supposed to be -19. So here we go. All I really care about is the sign. The sign will tell me everything we need. We don't care about the value per se. So when I'm doing the calculation, if I pick a value to plug back into f prime of x that's less than -1, let's say for example -2, the 6 is not going to do anything. So all I really care about is the two brackets. So if I plug in -2 into my first bracket, so we have -2 plus 1, I'm going to get a negative. If I plug in -2 into the second bracket, I have -2 subtract another 2, it's going to be negative. So my answer is going to be negative times negative, which is going to be a positive, which tells me it's increasing towards the function. So it's increasing towards the critical point. And for the next one, I'm going to pick a value between -1 and 2. Let's pick 0. So I'm going to have 1 times -2. So 1 is a positive value. -2 is going to be a negative value. So our multiplication will give us a negative. That means it's going down away from our critical point. So it's going to be decreasing. All right. And then we're going to pick a value greater than 3 for the last column. Greater than 2, I'll pick 3 for our last column. So we're going to have something like 4, which is a positive value, and 2, which is a positive value, and I want to get a positive total. That means it's increasing away from our critical point. So if we put that all together, the first one where x is less than -1, it's increasing towards our value. When we're doing x is between -1 and 2, it's decreasing towards the next one. So it's going to do something like a really big dip. And then we're going to have the last part where x is greater than 2, it's increasing away from our value. We don't know exactly where the x-intercepts are. We didn't calculate it, but if you want to do a more detailed sketch, we would have found our zeros first as well. Okay, so let me make a couple of notes here. So for the first part, we had f prime of x, which is greater than 0. For the second part, we had f prime of x, which is less than 0, means it goes down. And for the third part, we have f prime of x, which is greater than 0, and it's going back up. It matches up with the chart that we did. All right, we have a couple more to draw. So in this case here, lots of ways of doing this. The very first thing I'm going to do is I'm going to factor out an x squared, see if it gives me anything. I'm trying to do more detail on this one, right? So if I do f of x and I factor out an x squared, what we're going to get is x squared minus 8x plus 18. So, okay. And then I want to see if that's factorable. I'm trying the product and sum in my head. Two numbers will multiply together. It could be 8 to add together give me -9. It's going to be a combination of 8 and 1, 2 and 4. I can't get it. So what I'm going to do is I'm going to do something called discriminant. So discriminant, if you remember, is b squared minus 4ac. That's going to tell me if I should use the quadratic formula or if it's factorable, or we'll see what happens. So my b is going to be -8. I'm going to square that. Minus 4 times my a times my c. And when I do this, I get -8, which is less than 0, which implies that there's no roots. It's not factorable, right? So if that's the case, our graph is going to look something like this. Remember, hold on a second. Remember this part here? That's an order of 2. And that x-intercept's going to be at 0. So what does that mean for us? It means that I know we have an x-intercept of 0, 0. The rest, we know that a quartic can have 3 turning points. So we have two options for what our graph may look like. We may have something like this, or we may have something like that, right? I'm guessing it's going to be the first scenario based on the way the grid is laid out for us. But on a test, we wouldn't know this, right? We're going to rely on our calculations. So here we go. So we have f prime of x, which is equal to, I'm taking the derivative of the original function, not the factored function, right? 4x cubed minus 24x squared plus 36x. And once again, these are big numbers, so what I'm going to do is I'm going to factor whatever I can. So I think I can take out a 4x, and that leaves me with an x squared minus 6x plus 9. And I'm hoping that your factoring is still fresh in your mind. We can see that this here is a difference of squares. So we have f prime of x is equal to 4x, x minus 3 all squared. All right. So the next thing we got to do, let's highlight something here. Oops. We're going to highlight that. That's important, right? That's our new working function that we're using for all the calculations. Now, what I got to do is we got to set f prime of x equal to 0 when we have 0 is equal to 4x, x minus 3 all squared. And here we get x equals 0. And here we get x equal 3. Okay, and the next thing we're going to do is we're going to find out where these crazy points are. I'll put them underneath the graphic because we need some space. So if I do f of 0 and I plug it back in, we're going to see that the value is going to be 0. If I do f of 3, if I use my calculator, I do 3 to the exponent 4 minus 8 times 3 to the exponent 3 plus 18 times 3 to the exponent 2. My calculator gives me 27. And let's graph those. Well, we already have the 0, 0 graphed. Now we've got to do a 3 and 27. 3 and 27 is approximately here. So it's going to be at 3 and 27. So we can now see that this is not going to be the situation. It's going to be this one here. Okay, so let's make sure that our calculations support that. So I'm going to produce a little chart. So our little chart, let's take that out, make it a little bit lower. Okay, so we need one for the interval. We need one for the x critical point. I'm doing this one slightly different, and you'll see in a few seconds. Excuse me. And I'll do it in a different color so we can see that it stands out as well, right? So here we go. So we have our interval. Oops. Let's try this again. We have our interval. We're going to have f prime of x. We're going to have f of x. So this time what I'm going to do is I'm going to put my critical points on the top. So we have x equals 3, and we have x equal, sorry, the first lowest one is 0, so x equals 0. And my second is going to be x equals 3. We have to put it in increasing value, right, going along the top. And this first row, sorry, first column is going to be x is less than 0. This one is going to be where x is less than 3 but greater than 0. And the last one is where x is greater than 3. And we plug everything back into our highlighted function, here, right? And if I plug a value that's less than 0, for example, -1, what I get is -4. And no matter what value I plug into that bracket, it's going to be squared, so it's always going to be positive. So we're going to have something that's negative. So if it's negative, it's going to be decreasing towards x equals 0. So it's going to be decreasing towards x equals 0, right? And the next one at x equals 0 is a critical point. That's where it's going to be turning. If I choose a value between 0 and 3, let's say -1, sorry, positive 1, I'm going to have a positive times another positive because it's always positive in there. Positive, so it's going to be increasing away, and it's going to be increasing away to the next turning point. And the last one, if I put in a value that's greater than 3, I get a positive times another positive, which is still positive, which means still increasing. So it's going to be increasing right after that point there. It may or may not, we know that the square function, sorry, we know it's there's going to be a cubic function in there as well. I could have factored out an x and have a cubic, so this should really be something like a cubic function over there, right? We can actually do some more test values to see how to improve our graph. The basic shape of our graph will be something like that. For our next example, again, we're always looking for things that'll help us out. I know I can simplify the function as a difference of squares. That may help out, may not, all right? And we know that from the function above, we have vertical asymptotes. Our vertical asymptotes is x is equal to plus or minus 3. We have a horizontal asymptote. And a horizontal asymptote, because the degree of the numerator is less than that denominator, is y is equal to 0. If I try and solve for x-intercepts, I make h, so to solve for x-intercepts, we make y equal to 0 or h of x equal to 0. I cross multiply, there's going to give me a false answer, so there's no x-intercepts. And if I let x equal 0, we're going to have our y-intercept equal to, well, 0 and negative 1 over 9. So let's plot all that. So I plot my y-intercept, which is slightly below the y-axis, really hard to put. We have a vertical asymptotes, which is going to be at negative 3 and positive 3. And we have our horizontal asymptotes at x equals 0. All right. So the next thing we've got to do is start taking our derivative. So let's do this. So h prime of x is equal to derivative of the first, which is 0, times the second. And when I say first and second, I'm talking about numerator denominator. Subtract the numerator times the derivative of the denominator, which is basically 2x, all over x squared minus 9 squared. We know that h prime of x is equal to 0 when we have 0 is equal to, this all simplifies, right? That goes to 0, so we're left with negative 2x over x squared minus 9 all squared. Or we know that x in this case here could only be 0. If I plug in h of 0 and we solve for it, we know it's going to be our y-intercept we solved above, so there it is. So that means we're going to have 0 and negative 1 over 9 as a critical point. Since that's the only critical point, we're probably going to have to obey the rules of asymptotes. Hopefully the function doesn't cross the horizontal or the vertical asymptotes. We know for sure, it's never going to cross a vertical, but there's always the possibility of crossing the horizontal. So let's draw a little chart. And we need one for the interval. Hopefully that's enough. So let's fill this in. And again, we're working with the derivative function. So the derivative function that we're working with is really, I didn't clean it up, but it's really this part over here, right? Right, just we can put h of x instead of 0 there. So let's do this. So this is going to be our interval. This will be f prime of x. This will be f of x. This one's going to be x equals, the lowest one is -3 for our vertical asymptote. I did something slightly different there. X equals 0, x equals 3, our second vertical asymptote. If you want to get a better visual, you can just put that as a dash so we know that those are asymptotes, not critical points. So we know that these values will be when x is less than -3, x is going to be less than 0, but between 0 and 3. And x is going to be between 0 and 3 here again. That's -3. This one's going to be +3. And x is greater than 3. If we plug in a negative value into our function, remember the denominator is always going to be positive. So if I plug in a negative into the numerator, it's going to be positive over positive, which will produce a positive, means it's going to be increasing. And we have to check really a really big negative number, and what we'll see is that it's going to give me something looks like this. It's not going to cross the horizontal asymptote, nor is it going to cross the vertical asymptote. If we do a value between -3 and 0, let's say 1, the numerator is going to be negative, the denominator is always positive, it's going to be negative. So it means it's going to be decreasing. So it means we're going to have something that's going to be going, sorry, let's try that again. Negative means it's going to be positive. All right, positive means it's going to be increasing. So it's going to be something like this. Again, can't cross the vertical asymptote, it's increasing towards the critical point, which makes sense. If we put in a value between 0 and 3, let's say 1, that's when we get the negative. And it's going to be decreasing. And it makes sense. It's going to decrease from the critical point. It's never going to cross the asymptote. And if I plug in a value greater than 3, it's going to be decreasing, right? It's going to be negative. So in this case here, if it's decreasing, that means it can only be in quadrant 1 going down, right? Because if it was in quadrant 3 going up, it would be increasing, not decreasing. There's no way of decreasing from one quadrant without crossing the horizontal asymptote. And if it were to cross the horizontal asymptote, then we would have another x-intercept. So there we have a nice graph. And if we want more detail on the graph, we would pick some random values. For example, I'll probably solve for x equals -4, solve for its y value, maybe +4, maybe some other values in there to make them more detailed. But that's a good description of the graph. Excuse me. Given the graph f prime of x, find the critical points and intervals of decrease and increase. Sketch 2 possible graphs. I'm going to graph only one of them, just so we'll just go over the concepts, and you can use Desmos to play around with how many graphs you want to put on there. So what we're given in this case here is we're given f prime of x. So I'm going to write down the equation for f prime of x, and I'm taking the easy on you because this is a line, and the line is probably the easiest one to calculate for. We see that the y-intercept is equal to -2, and our slope would be this little right triangle here, which we're going up by 2, and we went over by 1, so it's going to be 2x plus 2. Now what we got to do is work backwards, and we have to find f of x. So really what we're doing is we're taking the antiderivative, or we're doing integration, which this is a very, very small flavor of what we'll be doing. We're not going to go into much more detail from that. And I got to figure out what the function would look like. So when I take its derivative, I get 2x. If I were to write x squared and take its derivative, I get 2x. Oops, I forgot. Sorry, I just noticed a little mistake here. Just change that sign to a negative. It's -2. If I want to get a -2, that means I have to take the derivative of -2x. But there's also the potential for a constant. So this constant here, all right, if we take the derivative of a constant, it goes to 0. Right? So if I pick a value for c, let's say for example 10, if I take the derivative of 10, I'm going to get 0. So that's why we're writing as a constant. I'm going to work with the easiest one. I'm going to say that f of x is equal to x squared minus 2x, and then assume that c is equal to 0, right? The way we'd actually figure it out is we'd actually have to plug in a point to actually calculate what that value would be, and we don't have more information, so just assume that's the case. And I'm going to do one more thing. I'm going to factor out an x. And what we can see is that we have our two x-intercepts. This here is x is equal to 0, and this is x is equal to 2. So I'm going to plot those down. Now, if you remember from quadratics, the x-intercepts somewhere in between the two, right in the middle, is the equation of the axis symmetry. So in that case, it falls in nicely over here. And if we think of the step pattern again, we know that if we start the vertex, we move over 1, then up whatever value, we'll get our first vertical step. I'm going to use that going backwards. We know that a is equal to 1. So if a is equal to 1, I'm going to go down 1, back 1, and I'll get my vertex. So if that's the case, so again, what I did is I went down 1 and back 1 because a is equal to 1, right? Or if you think about it, if I start the vertex, I go right 1, up 1, I land on the same point. So I kind of verified it. And then I go over 1, up 3, and it's symmetrical. So the distance from here to here is the same as the way back, right? So we have, I think, enough points, and I'm going to fit the curve the best way I can. And that's what one of the curves can look like in order to give me that f prime of x. You can use Desmos to play around with it. You can put the c and see what happens to it. Give me the same answer, right? For the next example, okay, it's a little more challenging. So let's take it from the beginning and see how far we'll go with it. Again, what we have here is we have two x-intercepts. So if I have two x-intercepts, I'm not really sure where the vertex is. I'm going to use the factored form. So we're going to have f prime of x, which is equal to a x minus r, x minus s. I'm going to plug in what I know. So we know that our x minus negative 1 is going to be plus 1, and x minus 2 is going to be the second part. And what I'm going to do is I'm going to plug in a value that I know for sure that's on the function. And I'm going to solve for a. So we have 4 is equal to a. I'm going to have 4 when I replace the x, and I have 2 when I replace the x. Sorry, and I have 3 when I replace the x. 3 minus 2 is 1. So that means our a value when we simplify is equal to 1. So our function, f prime of x, is really just x plus 1, x minus 2. If I expand this, what do we get? Well, we get f prime of x is equal to x squared minus 2 plus 1, so it's going to be minus x minus 2. So that's our function that we have there right now. I'm going to have to take its antiderivative now, right? So in order for me to get an x squared, and I'll do it down below, so when I have f of x, in order for me to get an x squared, I know when I have an x cubed. So when I drop to 3, I have to have something that cancels that out. Same thing, for me to get a negative x, I have to, well, there's only a negative, when I have to have an x squared. When I drop to 2, all right, I have to have something that cancels it out. And the last one, we can just add an x. Now, that's kind of tricky to graph. So I'll let you guys use Desmos to actually draw the graph. Obviously, it's going to be some kind of cubic. For example, number 4, sketch a graph of a function that is differentiable and satisfies the following conditions. These are beautiful test questions. So let's take it nice and slow. We can see that we have over here a point, right? The point that we have is negative 2 and 6. I can graph that, negative 2 and 6. I have another point, and in this case here, we have 1 and 2. Again, I'm going to graph that. And then I can't help but notice, actually, you know what? Let me take this. I can't help but notice that these two are the same, have some connections, and these two have some connections, right? So what this is really telling me is -2 and 6 is a critical point. And we have 1 and 0. F1 and 1 and 2 is another critical point. It tells me the slope is 0. Okay, so really what it means is technically we may, not necessarily, we have to do some more work, right? We may have vertical tangents at those points. Now, the second part is saying that f prime of x is greater than 0 when x is less than 2. So that means that our function is increasing towards that portion there. So f prime of x is greater than 0, so it's going to be increasing when x is less than -2. And then it says also increasing from this part over here. So this is f prime of x is greater than 0 when x is greater than 1. The last part is saying that it's decreasing. I can draw a nice graph, but we have f prime of x is less than 0 between -2 and 1. So I think that's a pretty good sketch. We don't have any more information to keep on expanding. So I think we're done. And this concludes lesson 4.2.